Okay, this is Physics 1C for November 12th. Tonight we're talking about LC circuits. In this picture here we have an LC circuit that contains an inductor and a capacitor. As I was just saying, the one thing that's different here is there's no battery, no EMF source. So in order to have any type of potential or energy of any kind, then we need to charge the capacitor plates to begin with. And then we'll do the kind of normal thing we do, which is this way in which we apply the loop rule, which really just means we're summing up voltages. And for our inductor, that voltage was negative L times di dt, where I is the current. And then for the capacitor, it's negative Q over C, where Q represents the charge at a moment in time, I represents the current at a moment in time. So yeah. And the idea is that these should all sum to 0. So what we'll do is we'll solve this equation just like we've done in the past. And the way we'll do that is to kind of say that we've defined in the past that electric current is related to a flow of charge, and the rate at which it flows is measured as kind of the derivative of the charge, the time rate of change of charge flowing through that circuit. So if we replace that in this equation here and move some things around a little bit, then this becomes the second derivative of charge. And move the Q over C to the right-hand side. Move the L to this side as well. And we'll get this expression that if we take the second derivative of the charge on the capacitor plate with respect to time, that this should be equal to a negative 1 divided by, getting ahead of myself, 1 divided by LC multiplied by the charge. Now our goal here, as with any kind of differential equation, is to solve for what is the charge as a function of time, or what is the current as a function of time. So these Q's here represent functions that we want to find. And the L and the C are constants that are related to whatever the value of L and C are. They could, in principle, be changed, but we're not thinking of them changing in time. They would just be the value of whatever inductor and capacitor that you put into your circuit. And when we look at an equation like this, it has the form of a differential equation that shows up quite frequently in, well, I would suspect in a lot of fields, but definitely in physics this shows up a lot. Because what this equation says is that we're looking for a function that when you take the derivative twice, you get the same function back, right? But you also get some coefficient here, and in particular, you get a negative sign. And that means that this has to be, really there's kind of three choices maybe you might say, of what type of a function that might be. And in order to kind of see it more clearly, I guess, what we normally do is we rewrite 1 over LC. Yeah, sine function is what someone says in the chats. That's exactly right. That's what we're going to get. We write 1 over LC as omega squared. This might be kind of weird. There's no square roots or squares of any kind in here, but that's what we do. And then we just say that we define omega to be equal to 1 over the square root of L times C. And we use that symbol because we kind of know in the end that what we're going to get out of this is a sine function. So then when we solve this equation, what we realize is that basically any function of this form and then you could also have, in principle, some kind of a phase constant. This isn't really important. It just represents a shift in the initial conditions of your system. And then in front of this, we'd have to have something that gives us charge. So the sign, this function itself, if you think about it, if you take the derivative once, then what you get, and actually maybe I should use the type of notation that you might see as you move on in your when we take a time derivative. I know in your calculus classes you always do like q prime is the derivative. So in physics what we do is we use prime if it's a spatial derivative, but we actually put a dot above the q if it's a time derivative, So what this means is basically you're taking the derivative of q with respect to time. When you put a dot like that up there, if you ever see that in textbooks, that's what they mean. So the derivative of this would obviously be cosine of omega t plus phi, but you would get an omega in front. And then when you take the derivative one more time, we take the second time derivative, which we represent with two dots. Sorry, there's two dots there. It doesn't look like the way it should. So it's a dot and then another dot. This derivative is going to be negative, and there's still going to be an omega there. The derivative of cosine would be sine. And then you'd have the derivative of the inside with respect to time, which would give you another omega. And if you compare this line right here with this line right here, then it definitely satisfies this equation, right? Because what you have here is that q of t multiplied by omega squared happens to be exactly equal to q double dot, right? It ends up being equal to this, right? This is exactly equal to the function q multiplied by what? Just omega squared, because the function q is sine of omega t, and that shows up right there. And so there we go. So now we know that this will work, except we're free to add anything we want to this system. And what we could add is we could put an overall constant in front right here. And what that constant needs to be is it needs to be the value of the charge at some point in time. Almost always that ends up being what we call kind of the maximum charge. And then that shows up on all of these equations too. I'll just multiply it to the end here. So this would be multiplied by Q max as well. And this is just whatever the maximum charge that the capacitor can hold will be. Right. Okay. All right, so that's one of the things we want to figure out. We'd also like to know something about the current as a function of time, but it turns out that we've kind of already got that right here. So this is going to be the current as a function of time. We can write it over here as a separate equation if we want to. The current as a function of time is going to be omega times Q max multiplied by cosine omega t plus phi. Okay, and so this actually tells us that this quantity right here has to be equal to the maximum current in the circuit, right? Because the cosine function varies from -1 to +1. So the maximum value that the cosine function can be is 1. So then omega times Q max has to be what the maximum current in the circuit is. So what's happening here, if we actually physically look at what's happening in the circuit, is that if we plot what the charge as a function of time looks like in the circuit, then we'd say that, well, it looks like a sine function, right? And maybe it's shifted by some phase. The phase that it's shifted by is going to depend on how the system begins, basically. But yeah. So what will happen here is that if we think about this Q as representing the charge on the left plate, let's say, then what's going to happen is the charge on the left plate is going to start off at, let's say it's a sine function, okay? It starts off at Q equal to 0, and it's a sine function, right? So it goes up like this. It reaches some maximum value of Q right here. That's positive Q max. And then that charge basically leaks off, and it reaches 0 again. And then the charge starts to go negative until eventually you've reached the maximum negative charge that you can hold on your plate. And then that process repeats itself again, heads back to 0, and then we go through one more phase again. The time that whole thing takes would be considered the period, and what that immediately shows you is that what's happening in this LC circuit is a type of oscillation of charges, right? The charge goes positive to 0 to negative to 0 to positive. So it's oscillating back and forth, and the rate at which it's oscillating is given by that little omega that's inside it there, and that's part of why we use the symbol omega for it. So this tells us this would be the radians per second for the oscillation, right? the angular frequency, so to speak. But we could also write down that if we take 2 pi divided by omega, then we could get what's called the period if we want to. That would be the time that it takes to go through one oscillation. And so that would be this time here, the time to go through one cycle. That would be the period, and that would be equal to 2 pi divided by omega. So we can talk about why this happens if we want to. I think is really kind of important to do. We can see the mathematics. We can see how the mathematics are arrived by using kind of this trick of using Kirchhoff's law. We said last time that really what's been done here is you're using Faraday's law and you're kind of cheating a little bit, but we know that it works, and we know that we get the right answer here for this. So I'm going to stop for a second and say, do you have any questions before we start going into the kind of how of what's going on here? How is it that we get this oscillation? Will charge be lost as heat? Sure. So this is a circuit that has no resistance, which means that the wires are made of superconductors, which, as you know, we haven't actually found wires that are made of superconductors. So that's already unrealistic. And the inductor itself is guaranteed to have resistance as well, and we did not include that in here, right? But the reality is that, yeah, absolutely, real wires will have resistance, and over time, even if you start off with some maximum charge, this process will not continue forever, right? Eventually, as the charge flows through the wire, it gives up some of its energy to the material, heats the wire up a little bit, right? So, yeah, absolutely. The idea here, this is like kind of a perfect idealized model of this, and we could even come over here and construct a really simple circuit of it if this thing will ever open. Shouldn't this have already opened? There it goes. And I think this provides a pretty nice visual of what's going on here with this thing. So all we really need is to grab an inductor and to grab a capacitor, and then just connect them up with wires, basically. And then as long as we charge up our inductor, we'll have exactly what we need. And I think that this is a pretty good animation of what's happening in the circuit, and a good way to visualize it. So again, we need to charge our capacitor. So let's do that with a switch, I guess. Ooh, there we go. And we'll connect a wire up here, and then we'll throw a battery in. We'll charge it up. Okay, it's charged. So now we don't need the battery anymore. So we'll disconnect it. And the capacitor will still stay charged even if... Okay, there we go. And there's our system. So you can watch it happen. It's this back and forth oscillation, right? Where you get this positively charged plate here. It drops to 0, and then it fills up with negative charges until it can't hold any more. And when I look at this, what I see is that these kind of little balls here, which are supposed to represent the charges, they kind of push their way onto this thing, and then this thing pushes back. And what is this? Well, it's a capacitor. And why does it push back? Well, because it can only hold so much charge, and once it's filled up with as much charge as it can fill with, then it kind of pushes back, right? Now, it's important to compare what's happening here to a simpler system so we can understand why this is different. So if we take a system and we do not have a... let's charge this up. All right. So if I take a system and all I have is this charged capacitor, right? And what I do is I then connect up a circuit, but I don't have... Oops, didn't do that. So if I connect up a circuit, but I don't have an inductor in it, how did I get 2 of those? If I don't have an inductor inside of it, what's going to happen? Will the charges keep flowing like they do there? If I close this, are the charges going to go back and forth? Okay, you're saying it. I think you're trying to say it stops, right? Yeah. Yeah. So by doing this, we're just going to discharge the capacitor, right? So what's the difference? Well, obviously the difference is the inductor, right? But why does the inductor make it work like this? Why does the inductor make it so that these charges can basically kind of continuously flow back and forth and back and forth? Let's chart this up again. There we go. Yeah, why does the inductor do that? The energy that comes and stored in the inductor's magnetic field. Yeah, that's a good way of thinking about it. So you start off with energy stored in an electric field. That energy then kind of goes directly into the inductor, which stores the dense magnetic field. And then the magnetic field of the inductor can then basically keep the charges going effectively, right? So an inductor has the effect of stopping you from having... Oh, and we can also do one other thing with this here too. I can pull this current chart in here, and we can see that this is like sinusoidal if we want to. Just like that. So I'll let that go over there on the left, but I mean, the idea is basically that current starts to flow, and that current eventually is going to stop, right? But the inductor kind of tends to make it keep going. Yeah, that's a really good analogy. That's right, Miaras, is that it's basically like you have energy stored up in the spring that is the capacitor, and then as the charges flow, they gain a type of kinetic energy that they maintain. And that kinetic energy gets turned into potential energy, and then back into kinetic, and back into potential, and vice versa, just going back and forth. So the analogy for this is the spring mass system that you learn about in Physics 1A, where, just to remind you of what that is, I don't know why that opened. I think I clicked it by accident. So in mechanics, what you learn about is you learn about this system where you take a mass and you put it on a frictionless table. Frictionless in this case is corresponding to the fact that there's no resistor in our system. You have a mass and you have a spring, and it has some spring constant. These are the two parameters of your system, mass and spring constant. Just like in our system, we had length and capacitance. Not length, sorry, inductance and capacitance. And then what you do is you basically you pull it out to some point here, your mass. You stretch it out to some point here, which causes the spring to stretch out, and then you just let it go, and the mass basically oscillates back and forth, and the rate at which it oscillates is a function of the parameters of the system. Square root of k over m here, and the one that we just got was omega is 1 over the square root of L times c. So L corresponds to mass, and capacitance is kind of similar to the kind of inverse of the spring constant, basically. But yeah, there's your LC circuit. There's a nice thing that your book does here, which kind of visualizes all the kind of stages of this process, I guess, so you can understand what's happening in terms of the energy, as Ash pointed out. So it's a repetitive process. It goes through one full oscillation in this picture right here. So at t equal to 0, we start off with maximum charge on the capacitor, right? Qm represents maximum charge. You close this switch, and the current starts to flow in this direction. It flows until there's no more charges left on the capacitor plates, at which point, with current flowing through these little wires right here, you've developed a magnetic field. So your energy went from being fully electrical, UE, into fully magnetic. The time at which this this is going to occur, that is when the charge on the plate is 0, is going to occur at t over 4, 1/4 of the period. The inductor is going to make it so that even though there's no source to make this current keep going, and the current will tend to die down, the inductor will make sure that doesn't happen too quickly. So the current will kind of continue to flow as the magnetic field decays, but the current is decreasing at that time. But all the while that it's decreasing, it's piling up charges on the plate right here. And that'll occur up until the point when the current doesn't flow anymore. When there's no current flowing, you've reached the point when you've got the maximum voltage on your capacitor again, except that it's the polarity is reversed now. Here it was positive, negative, and here now it's negative, positive. But then now you've got this tense capacitor here that's storing up this energy and has to give it back. So the capacitor discharges, which causes the current to flow again. And that current will basically flow until there's no charges on this capacitor, but the current will kind of continue to flow because, again, that current has a type of kinetic energy, momentum, however you want to put it, or inertia, due to the fact that there's this inductor here that has a magnetic field, and that magnetic field can basically deliver energy back to the system, charging at the capacitor plate back to the initial state. So you go all the way back around to the beginning again. And there we go. Anyone have any questions? So we can kind of investigate the time nature of this if you want to as well, because we said that you get this omega equal to the 1 over the square root of LC. So I think what we can do is on our on this picture right here, what we could do is we could alternate. We could change the values of these things. So this starts off at 0.1 farads and 50 henries. So can you all tell me what would the value of, is this going to be easy to calculate? Not exactly, but it'll be close enough. What would the value of the omega be for this system here? Where you do 1 over square root LC. 1 over the square root of 5, yeah, exactly. So if we wanted to increase the frequency by a factor of 2, what could we do? Do we need to decrease these quantities or increase? Multiply, but we need to decrease them by a factor of 4, right? So how could we do that? 0.1 can only go down to 0.05, so that's a factor of 2, right? And then if we get this one to go down by a factor of 2 as well, then that'll work as well, right? Yeah, we want to double the speed, basically, right? So if we get a 25 here, and then we let it play again, you can kind of see it on the graph here. I don't know if you can tell very much from looking at it, though. And the smaller we make these things, let's pause it again when it's, the larger the value of the frequency is going to be. So if we make these as small as we possibly can, take this one down to 10. That one's already at the minimum. You can immediately see that the curve gets a really much faster frequency, right? We've also altered the peak to peak here, which means we've altered in some way the amount of energy stored in the system too. Okay, so that's an LC circuit. Anyone have any questions? The fact that there's a frequency here, we're going to refer to this quantity here to be what we call kind of the natural frequency. And that's relevant because at the core of what an LC circuit is kind of the ability to actually send information and receive information along these frequencies. So it turns out that if you have a circuit that's designed like this, and you put another circuit that's similar to it in the same room, you can actually send signals between them. All right, and the way that that works is it's pretty straightforward, I guess. Imagine that you have one circuit right here, and in your circuit you have an LC circuit, right? And this LC circuit, let's say, starts off positive here, negative here, right? It has a capacitance C and inductance L, okay? And then nearby, if I place another, let's say, uncharged capacitor, so this one starts off uncharged, but let's say that we give it the same L and the same C, so they have exactly the same values. than what a guy named Heinrich Hertz. Hertz is a name that you're probably familiar with through. Well, there's like an automobile company that's named Hertz, right? That's a different thing. There's also the measurement of frequency that we use is hertz, right? You talk about the frequencies that your cell phone uses, it's like gigahertz. The frequencies of radios is like megahertz and kilohertz, right? It's how we measure frequency, right? So Hertz figured out that you could actually transmit a signal, that the fact that this system right here on the left would have this kind of oscillating charge can basically kind of send a signal somehow through the air. And it can be picked up by this circuit on the right, so that this one can become like kind of a transmitter, and this one can become a receiver. And the key thing is just that they're tuned to the same value of L and C. They both have the same kind of natural frequency. The actual fact of what's happening is that by these charges accelerating within the system here, I mean, if you think about an individual charge within the system here, it's basically oscillating this way and then that way and then this way and then back. There's oscillating back and forth and back and forth. That actually has the effect of producing what are called electromagnetic waves. And these waves are enough to basically induce a similar type of signal within the system on the right. And Hertz figured that out. In addition, he figured out, not only did he figure this out, but he was able to prove that the waves that were produced were subject to all the same normal constraints that light waves are subject to, meaning that the speed of these waves was the same as the speed of light. He was able to measure that by measuring the wavelength and knowing the frequency, because you can use the fact that C is equal to lambda times frequency. He was able to use this. He calculated the wavelength of these waves by reflecting them, actually, and setting up what are called standing waves. If you've taken Physics 2A or Physics 1B, then you probably know something about standing waves. And so he was able to basically reflect these waves between 2 points and figure out exactly how long their wavelength was by forcing them to kind of reflect back like this. And if you don't know what a standing wave is what occurs when you pluck a guitar string, actually. It's a type of wave that basically bounces back and forth between a point and kind of oscillates and vibrates up and down like this, basically, right? So he was able to measure lambda, and he knew the frequency, because the frequency is equal to, well, we just figured it out a second ago. It's 1 over the square root of LC, except this is in radians per second, so you need to divide by 2 pi, I believe. Right? So this he could calculate, because he knew the inductance and the capacitance, right? And he could find the frequency, and he could find the wavelength, and he could prove that these waves that were happening in his laboratory, they traveled at the speed of light, which was known pretty well at that time. This is a discovery that occurred, I want to say, in like 1880, could be 1889, I don't remember. Sometime in the 1880s is when this occurred. So this is after Maxwell. Maxwell was 1865. This is 15 years later, maybe a little bit more, that Hertz figured this out. Maxwell actually predicted that you would see this type of effect, so it makes sense that Hertz is looking to produce it, right? Maxwell predicted the existence of electromagnetic waves. Hertz then proved it by using this kind of LC transmitter receiver type of system here. And I should be a little more clear about what he actually did. What he did was he used a system where there were basically, he had like a spark discharge gap. I'm sorry, I'm going to sneeze 1 second. Sorry. So, anyway, so that's effectively how a radio works. Is it works off of kind of tuning in. Thank you. It works off of tuning in to a signal to pick up the signal, right? And the way that you do that is you basically just change these quantities, L and C. By changing those, you can affect the frequency. So all you really need is a type of variable capacitor. A variable capacitor could be something in which the plates, basically you just pull them in and out from each other. Or you could have a variable inductor. A variable inductor, what they often do is there will be like an iron core. And what you do is you input the iron core into the inductor, but maybe only up to a certain point. And then the distance that you move the piece of iron in and out will actually cause L to change. Does that make sense? The iron basically makes it so that the inductor works better. than it normally would once you put it inside of there. And so you can have kind of a variable inductor, and as long as your inductors is varying in some way, then you have the ability to change your frequency. At the end of the day, if you think about like older radios where you have to like tune into a station with a knob, that knob is directly connected to something like this, to a little piece of iron that's sliding in and out of a solenoid. If you can believe it, that's all that's happening, is this little piece of iron is sliding into or out of the solenoid, and it's altering the inductance, which then alters the channel that you're tuned into, right? Does that all make sense? Did I go through too many things at once? I don't know. You might have any questions? It could also be a variable capacitor too. It's just one of the two. You have to find a way to vary one of these. Yeah. But anyway, I'll wait for questions. If we don't have any questions, we'll just do a problem real quick. And all right. A 300 volt power supply is used to charge a 25 microfarad capacitor. After the capacitor is fully charged, it is disconnected from the power supply and connected across a 10 millihenry inductor. The resistance in the circuit is negligible. Find the frequency and period of oscillation of the circuit, and find the capacitor charge and the circuit current 1.2 milliseconds after the inductor and capacitor are connected. I just realized something that I think is worth going back and talking about. So one of the things that Ash said was he said, would this eventually kind of like, how did you put it? You said, will the charge be lost as heat? Yeah. So I should have mentioned as well that even if you have a perfect system like this, because of the fact that it can emit radio waves, it would eventually run out of energy even if it was made of superconductors. Because that's a type of energy, right? Does that make sense? It would eventually run out of energy. It would go forever if it wasn't for these electromagnetic waves, but this is the waves themselves are another phenomenon that we still kind of need to develop, and there's a whole chapter on electromagnetic waves, but yeah. Okay, so oscillating circuit. Okay, so we have the capacitor's charged up to 300 volts, and it has a capacitance of 25 microfarads. We also know that we have an inductor that has 10 millihenries, so that's 0.010 henries. Part A, we want to find the frequency and period of oscillation of the circuit. So we said that the frequency for the oscillation would be 1 over 2 pi times 1 over square root LC. So that's going to be 1 over 2 pi, and then the square root of L is 0.01 henries multiplied by 25 times 10 to the negative 6 farads. If y'all could calculate what that is. So we could do this pretty easily, but the 2 pi part's going to throw me off. Because it's going to be like 1, 2. Yeah, I think this is what you're going to get, but then I don't know what this is, so I have to calculate that. The units for this are going to be in seconds, or sorry, hertz. The denominator would be in seconds. Did you get 1,000? Is that what you got? 318. That sounds more correct to me. Is that what other people got too? Anybody else? It's 318, okay. All right. So that's going to be the frequency. To find the period is just 1 divided by the frequency. So 1 over that. What do you get if you do that? Some of these simple calculations I should probably just do, but I don't think my phone's there. There's my phone. 0.00314. Okay. Yeah, that makes sense because it's coming from something times pi. So that's the seconds. That's how many seconds it takes to go through one oscillation. That's really fast, right? All right. And then part B, find the capacitor charge and the circuit current 1.2 milliseconds after the inductor and capacitor are connected. Okay, so for this we're going to need to think about some of the information that was given. First of all, we know that the system starts off in the following state when it's first charged. You have a capacitor that's charged to 300 volts. You're initially connecting it directly up to an inductor. And at that time, we're going to say, for example, that you have positive Qmax on this side and negative Qmax on this side, right, when we connect it up. And we're going to be thinking about basically just the charge on this plate on the left. And we have this expression that we wrote down before. But now we get to be really kind of more specific about how we write down our expression. So what I used before was, I think, a sine function, right? In this case, if we were to go ahead and kind of plot what's going to happen in our system, at t equal to 0, the charge starts off at the maximum, right? And then it kind of oscillates like this. So at t equal to 0, we know we're right here. So I'm going to use a cosine function. Just because that kind of seems to kind of sync up with the initial conditions, right? Does that make sense? Because at t equal to 0, then, this is going to tell us that q of 0 is equal to q max, which is what we want. Okay. Our goal is to find the capacitor charge and the circuit current 1.2 milliseconds after they're connected. So let's do that. When would we use sine? We could use sine here as well, but we would have to use a sine function that was shifted a little bit. So we do like sine of omega t minus pi over 2, for example, or maybe plus. But yeah, the fact is that sine and cosine are really just they're the same function. They're just shifted by, a little bit. So just whichever one works. So let's plug in some values here. So q max is going to be equal to basically just the capacitance multiplied by the potential difference. So that's equal to 25 microfarad multiplied by 300 volts. And then cosine of omega t. So omega is the one that is 2 pi times the frequency. So this is going to be 2 pi multiplied by the frequency, which is 318. Maybe there's an easier way to write this, because it's basically 0.2 times 10 to the 4. Well, it's 2 pi multiplied by 318. And that's multiplied by t. Here, let me actually calculate what some of these things are here. Yeah, so 2,000. And then the other one will be 0.0075. Well, I need to... That's not quite right now. Now it's going to be radians per second technically, but oops. Okay, so that's the charge as a function of time, and our goal was to find the capacitor charge 1.2 milliseconds later, so we just need to plug in Q at 1.2 times 10 to the minus 3 seconds. I did. Do we have to convert the microfarads? I did. If you didn't convert it, it would just have, this would just be like 750 microcoulombs. That would be a perfectly reasonable way to write it. Yeah, 7.5 millicoulombs would work too. So that'll give us the charge. I'll let y'all calculate what that's equal to. And then if we want to get the current at that time, we need to take the derivative of this. So then the current as a function of time is going to be the derivative of this. So that'll be negative 0.0075 5 coulombs multiplied by the inside derivative, which is going to be 2,000. And then this will become a sine function. Is that like okay to everyone? What do you all get for the answer for the charge? Yeah, so why do we get this almost the exact same value that we have in the front here then? Did you guys, one other thing, did you put it into radians, your calculator, when you did this one? I tried in radians. Okay, that looks like a good answer. Did everybody else get the same thing? Great. And then for the current, we do the same thing. We just plug in the same thing into the current equation, which has that sign in it. Let's see what we get. So I got negative 10.1. Do y'all get the same thing? Yeah, same thing. So for this one, we're using that equation. Anyone else get the same thing? Okay, cool. All right, any questions about LC circuits? So the last topic is Lrc circuits, and these are really similar to what we just saw here. The main difference is, here I'll pause this whenever we get to one of the kind of maximum or minimum peaks. The main difference now is just that the energy is going to be rapidly translated. Interesting how the units work out perfectly. Yeah. That is interesting. So now what's going to happen is the energy in our system, right, is going to start to be dissipated by this resistor, and it'll probably happen pretty quickly in this system right here. Let's check it out. So if I push play, what'll happen is our sine wave is now going to become kind of a... It's going to kind of dampen out, basically. There's still some little wave characteristics there. And I'm sure if we zoom in far enough, we can still see it. But basically, it's going to trend down until there's no more current flowing in our system anymore. Right? So if we want to kind of think about how that's happening on this page over here, when we connect up an Lrc circuit, you have resistor, inductor, capacitor, R, L, C. And again, this is a circuit where we say that the only source of energy that we're going to work with to start off with is that we just start off with the capacitor charged. And what ends up happening here is that you get a curve that is kind of damped out by a kind of exponential decay. So that when you plot like the charge or the current as a function of time, what it'll do is do something like this. It'll still be kind of a sine function. It'll actually still even have the exact same frequency. But it'll just kind of damp out over time like that. And apart from showing it to you and suggesting, you can go read in the textbook if you want to read about like the units that are associated with this, but the equation that's associated with this. But it's something like you have like an exponential function that has like I think it's like e to the negative RT over 2L or something like that, and then there's an amplitude, and then it's multiplied by, again, like a cosine function. But then the frequency is quite a bit different. It has a resistance in it, and I don't think you have any specific problems where you have to use this. But anyway, that's an RLC circuit. The thing I will say about this is the RLC circuit alone it's kind of not very interesting, except the fact that the resistor has the effect of kind of causing the energy of the system to kind of slowly get converted into heat over time, right? What is interesting is thinking about what would happen if you attached a type of power source into your circuit, and this is what we're going to be talking about for the next few weeks, or the next week or so. If you introduce what's called an alternating current like power source, then the LRC circuit becomes a lot more interesting, because what an AC power source does is it basically pushes the current to the left and then to the right and then left and then right and then left and then right. And what this can do is it can make it so that the current keeps flowing within a system like this. And that's what we'll be talking about for the next week or so, is what happens when you connect an AC power source up to a system like this. And yeah, kind of a shorter lecture tonight, but that's really it. That's the end of that chapter. You have any questions? So the LRC has current going back and forth, and the LC has charges going back and forth. Yeah, they both do. Yep. They both do.